Hi everyone. Today we are going to take what we've learned about igneous rock types, and mineral lava types, and start thinking about volcanoes themselves. So we'll go over some of the features that are commonly seen along with volcanoes, as well as type of volcanoes and some hazards that are caused by volcanoes. So by the end of this lecture, you'll be able to determine between different types of volcanoes. You'll be able to explain how volcanoes can produce such a variety of materials, and then connect the eruption type with the type of lava that you're looking at, as well as explain some of the common hazards, as well as the predictability of future eruptions. So for example, I have two different volcanoes to look at. We're going to see the different types of volcanoes that can exist. So this is Mount St. Helens in Washington. It erupted in 1980. It had very, very deadly pyroclastic flows, which were gases, hot ash, and rocks, as well as lahars, which are volcanic mud flows. And it killed 59 people. So this is what the volcano looked like before. And this is what the volcano looked like after. So it really exploded the whole top of this mountain off. So here I have a video to show you a little bit about this. So that was a very, very explosive volcanic eruption, and very, very different from this other example, which is in Hawaii. So this is considered the world's most active volcano. However, it is not at all as explosive as something like Mount St. Helens. So currently, it has erupted about 3.1 cubic kilometers of lava. The explosive part of these eruptions are incredibly rare. It is more like it is just leaking lava. So I have a video example of this as well.
For the past couple of weeks, this river of red-hot rock has been causing chaos in the streets of Hawaii.
So notice how slowly it's moving.
The lava doesn't move quickly, but nothing can stop it. And as you can see from this video, it destroys everything in its path. The lava is coming from Kilauea, a volcano on Hawaii's Big Island, which is home to these guys.
Aloha BTN, I'm Fiona.
Aloha BTN, my name is Sebastian.
I go to Volcano School of Arts and Sciences. It's about maybe a 4-minute car ride / bike ride to the national park, also to the crater. Right now the lava is causing people to evacuate.
So that video is linked if you want to watch the rest. But you'll notice that eruption style is completely different than Mount St. Helens. So you can see there were people there picking up with instruments, picking up the lava, taking pictures of the eruption. Whereas with Mount St. Helens, that was definitely not the same situation. So when we think about volcanoes and eruptions, the main three products from a volcanic eruption are lava flows, pyroclastic debris, and volcanic gases. So lava flows is, of course, a flow of lava. Pyroclastic debris is any other debris that would be erupted, and then volcanic gases are definitely always released into the air. So volcanic gases can sometimes, when they are, when it's a very serious eruption, they can actually reach all the way up into our stratosphere. So above where our planes fly, reach up into our stratosphere. When that happens, we can get those gases spreading across the hemisphere and across the world very, very quickly. And we'll have what is called stratospheric haze. So it can actually cause some global cooling and some very cloudy years from these really bad volcanic eruptions. So first, we can look at lava flows. So lava can come in many different forms. So we can have really thin and runny lava, or thick and sticky lava. Now, the difference depends on viscosity, or the thickness of the material, which is determined by the composition of the magma or the lava, which is the silica content. So remember, felsic versus mafic. It can also be determined a bit by temperature, but mostly the silica content is what we care about. So the viscosity, we can see here, very low viscosity. We're going to have flowing basaltic lava. As our viscosity increases, this is where we have more felsic material. So this is where this material is not runny or thin at all. It is thick, it is sticky, it is not going to erupt like the Hawaiian eruption. It's going to be more of an explosion there. It can actually cause a dome that clogs up the top of the volcano. So basaltic lava flows are very mafic. They're hot, they're low viscosity, they're flowing, they're thin and more fluid, so they can flow very, very long distances. And like the video that I showed said, it can't be stopped. So lava flows like this are something that cannot be stopped. They can move about 30 kilometers per hour if they're on steep slopes. So I do not know these people, but I found it pretty funny that on their vacation they decided to take a photo in front of the flowing lava. As you can see, this basalt lava flow, this very mafic lava flow, is not a huge danger to you if you're able to get out of the way. So for example, they stopped, they took this picture, they're probably going to walk back to their car and hopefully drive in the other direction. So once it starts flowing, it can't really be stopped, but it does move very slowly. So evacuation is something that can be used very successfully, for example. We can also have basaltic lava underwater. So for example, at our mid-ocean ridges, we call this pillow basalt. So we generally have these round blobs of basalt. They cool quickly because they're in water. So it's going to cool these sort of mounds or pillows. So this is really common at our mid-ocean ridge, as you'll see pillows of basalt. I have this video to show you. So as it cools in that blob shape. It cools very, very quickly because it's in contact with the ocean. So it causes that pillow shape. That's why we call it pillow basalt. So you really only see pillow basalt underwater. So you can also have lava tubes. So lava tubes are just conduits for basaltic lava. So different tubes or pipes, let's say, where lava would have flown at one point. So here we can see there's a hole actually into one of the lava tubes, so you can look over the edge and look in at the lava. So those are all associated with basaltic lava, or very mafic lava that is very flowy and thin. Now we have andesitic lava. So andesite is another type of intermediate igneous rock. So andesitic lava has a bit higher silica content than basalt. So it makes the andesitic lava a little more viscous. So it does not flow rapidly. It does flow a bit. So andesitic lava will often sort of mound around the vent of the volcano. It might flow a little bit, but it doesn't flow the way that the basaltic magma does. So this isn't going to flow very far from the volcano at all. It'll maybe move 1 to 5 miles per day, and it's often very blocky lava. So it's thick, blocky lava. It's not smoothly flowing lava that you would see with a basaltic lava. So we also can have rhyolitic lava flows. So rhyolite, another igneous rock. Rhyolitic lava flows have the highest silica content. They are the most viscous. So this lava does not flow at all. It generally plugs up the lava dome. The lava vent, creating a dome. So here we have this rhyolite dome. So this dome of rhyolite that is formed at the top of this volcano. This is a cartoon version of that. So this is the dome that when it solidifies, it can often plug up the top of the volcano. So at the next time of eruption, this is often exploded in a very, very violent explosion or eruption there, because it doesn't flow away from the volcano, it just mounds there at the top. So volatile content, where we have a higher silica content in the magma, that means there's also a higher proportion of gas in the magma. So where we have very high pressure, the gases will be dissolved. Where we have lower pressure, the gases are going to form a vapor. So the thing is, the high viscosity doesn't allow gases to escape. So in a very high viscosity magma, the gases are all trapped within that magma. Whereas with a low viscosity magma, those gases can move up through the more flowy material, and that volcano can be degassing, letting off little bits of gas over time. That high viscosity magma traps all of the gases within the magma, so when there is finally an eruption, you're not only erupting that magma, you're erupting all of the gaseous material that was trapped in the magma as well. So those, for example, the rhyolitic lava flows, very, very viscous. All of the gas material is going to be trapped within, mixed in with this lava. So when we do have one of these explosions, it's going to be a very explosive eruption with a lot of gas and volcanic gas emitted into the atmosphere all at the same time. So we can also have pyroclastic debris. So generally when this is basaltic, the lava fountain here will have gas bubbles and it will burst near the surface. So we can have these little bits of lava, which when they solidify, we call them bombs. So it can be little bits of lava that can solidify midair and then come crashing down as solid rock. Either bombs or blocks. So bombs being solidified blobs of lava, or blocks being already solidified lava that's picked up and thrown by the eruption. So in our eruption, we don't only have lava flows, but we also have flying rocks. Some of them are brand new. Some of them are part of the volcano that was actually picked up and thrown by the eruption. With more andesitic or rhyolitic pyroclastic debris, we're going to have more explosive eruptions. So it's with the basalt, the last slide, that's where we have more of the immediately forming rock. It's a much flowier lava, whereas with the andesite and the rhyolite, these are our intermediate and felsic magmas, so they erupt much more explosively. So we have more viscous material, so it's not going to flow as easily. We know that that material is also going to contain a lot of gas because the gas cannot escape. These volcanic eruptions often produce a huge quantity of volcanic ash. So not only are we releasing tons of gases as well as magma material, but also volcanic ash. So that volcanic ash can rise up very quickly and then can spread very far distances, falling kind of like snow, for example, all over this town. You can see this is all volcanic ash there. So we can also see pyroclastic flows. So pyroclastic flows is essentially an avalanche of ash. So unbelievably hot ash rushing down the face of the volcano. They can move incredibly quickly and essentially incinerate everything in their path. So pyroclastic flows can be absolutely terrifying. Here we have this pyroclastic flow. It is the hot ash rushing down the side of the volcano. We also have ash that's been emitted directly into the air, which this is forming an ash cloud here. So I have one more video for you guys of a pyroclastic flow.
Something triggers a pyroclastic flow about 10 times bigger than all that came before. Within moments, it overwhelms the valley. By the time a TV camera in the village records this scene, Maurice, Katya, and 41 others are dead.
So pyroclastic flows of that type can be absolutely horrible. Some of the deadliest parts of volcanic eruptions because they move so quickly. They're pretty unavoidable. So if you ever see one, you better start running really fast away from the volcano as fast as possible. In addition to gaseous flows, we can also have wet volcanic debris. So volcanic debris flows can actually mix with water. So where we have a pyroclastic flow or volcanic ash, it can actually mix with, say, a river that was already there, or a volcano that had snow and ice at the top because it's quite tall. It can immediately melt, mix with all of this material. It becomes a muddy ash, so it's very muddy. We call this a lahar. So this is a photo here of a lahar that took up this river valley. So all of the, some of the volcanic material actually mixed in with that water, creating an incredibly difficult to remove lahar. This is in New Zealand. So when we're looking at volcanoes, there are a couple of specific terms that you should know. The magma chamber, which we've talked about here, that's important to understand. We have the magma chamber and then the conduit up to the top of the volcano. You'll notice that we have some of our igneous rock features labeled here. We have sills and dikes, the vertical versus the horizontal bits of igneous rock. We also have our lava flows. So here's a lava flow. Here they're showing a lahar. So you have the debris from the volcano flowing down that river valley. Here we have a laccolith, which is causing that doming on the surface of the earth. Those are probably the most important terms for you to know. Fracturing is where you have cracking in the rock. You should know ash. So we have ash exploding from the volcano up into the air, and also our pyroclastic flow, which is flowing downslope very quickly. So there are 3 different types of volcanoes that we are going to talk about: shield volcanoes, cinder cone volcanoes, and stratovolcanoes. So shield volcanoes are generally very big, they're broad, they're very gentle slopes. This is a cartoon of our shield volcano. They're made up of layers and layers of lava that has solidified as that mountain gets bigger. Cinder cone volcanoes are usually very cone-shaped, and they're made of piles of basaltic rock, not as flowing or broad or gentle as the shield volcano. Stratovolcanoes are the largest volcanoes. They're often sometimes called composite volcanoes. They're very large, and they're layered generally with both lava and debris layers. So strato, the word stratovolcano comes from strato, which means that there's internal layering. So there's layering of lava, and then debris, and then lava, and then debris, creating a composite volcano. So here's an example of a shield volcano. So this is so large and broad. This is in Hawaii. So it's a really large, gentle, sweeping slope. Nothing like a steep mountain. So it's created because the layers of lava spread out. So this would be basaltic lava. It's going to reach the surface and then spread out over the surface of that volcano. So the volcano will grow, but it is not at all steep. It is much more broad. Cinder cone volcanoes are quite small, but they really are cone-shaped. So they are generally piles of rocks instead of looking solid. They look like piles of rocks. So generally they're made from eruptions that cause a lot of ejected fragments. So lots of little fragments of rock. So they're generally very symmetric, very cone-shaped, and they have a crater at the center. So these can, when there's a very strong eruption here, they can actually be completely exploded, leaving behind what we call a caldera, or a sort of a big crater where the volcano used to be. And then the last type is a stratovolcano. So these are the largest volcanoes. They're generally very, very tall, and they're going to be layered with both debris and lava. So our shield volcanoes are made of essentially just layers of lava. The cinder cone volcanoes are made of all types of debris. The stratovolcanoes are layered of debris and lava, and they are generally very, very tall. So this is Mount Fuji in Japan, a very tall, classic-looking stratovolcano. So we can have two different types of eruption, effusive or explosive. So explosive is where we have our pyroclastic debris, blasts in the air. Effusive is where you're going to have your basaltic, very low viscosity magma sort of pouring out steadily of the volcano instead of a big, massive explosion. So there's two different types. So where do we see our volcanoes? Same places that we went over where we see our igneous rock, because anywhere that we have volcanoes, we're going to have igneous rock. So plate boundaries, hotspots, and rifts. Mid-ocean ridges, convergent boundaries, hotspots, both oceanic hotspots and continental hotspots, we will see volcanoes. So anywhere that we have magma reaching up to the surface and then lava erupting on the surface, we have volcanoes. So they can come in any three of those types of volcanoes. So here we have our mid-ocean ridge. The mid-ocean ridge has created about 70% of the mid-ocean ridges in total have created about 70% of our Earth's surface. So this is where we're going to have basaltic material being created. Remember, our ocean crust is basalt, and that melting is caused by decompression. At convergent boundaries, of course, we have that flux melting where we have subduction. This is going to create island arcs, which are going to be basalt. So when we have continental crust melting here and then rising up through more this is oceanic crust. Oceanic crust melting, rising up through more oceanic crust, we are going to have a very basaltic island arc because the material is just melted oceanic crust. Where we have ocean to continent, we have oceanic crust melting. That melt is going to rise up through our continental crust. So as it rises up through, we're going to have contact melting. So some of that continental crust is going to melt, and that eruption is going to be more of an intermediate magma. So instead of being completely mafic, completely basalt, we're going to have more of an intermediate magma, more like andesite, because our mafic basalt oceanic crust melts and then rises up and combines with our very felsic continental crust. So where we have that combination, we're going to have more of an intermediate magma there. Hot spots, of course. For example, we can have two types, oceanic or continental. So an oceanic hotspot would be Hawaii, as an example. And then we also have continental hotspots. So, for example, Yellowstone. So, in an oceanic hotspot, we would expect to have basaltic magma because we are looking just at oceanic crust. However, at a continental hotspot, we would expect intermediate or felsic magma because we are erupting continental crust. So, that continental crust is mixing, mostly due to heat transfer of the magma chamber beneath. So we're going to have more of an intermediate or felsic magma there with continental hotspots erupting. So when we think about volcanoes, there are quite a few hazards to go along with them. Some of them we've mentioned already. One thing to always think about is reoccurrence. So an active volcano is in a volcano that is actively erupting. It's recently erupted, or it's likely to erupt anytime soon. A dormant volcano is one that we consider that hasn't erupted in hundreds to thousands of years. An extinct volcano is a volcano that's no longer capable of erupting. So if you were to buy a home, for example, I would stick with staying near an extinct or dormant volcano if you had to choose one of the three. Active volcano can be very, very dangerous, as we have talked about. Dormant volcano doesn't mean that it isn't going to erupt. It just means that it hasn't in hundreds to thousands of years. So how about predictability? Can we predict volcanic eruptions? In the long term, no. It's completely impossible. We have no way of predicting eruptions. However, there are some warning signs. So often when there is a volcano that is getting ready to erupt, that magma is moving upwards, there's increased earthquake activity. So that magma moving in that volcano is causing earthquakes. There's often changes in heat flow. There'll be increased heat flow because there's more magma present near the surface, as well as changing in shape. So magma can fill up chambers, move further up, causing changes in the shape of the surface, as well as increased gas emissions. So if there's increased gases bubbling out, we can expect that there's more. Magma reaching the surface. However, these things don't usually happen together, and they can all also happen separately. So it's often the warning signs are not always seen as a warning. It's more, in hindsight, that explains why there was increased earthquake activity, or in hindsight, that does explain why there was increased heat flow. But if there's increased heat flow, you aren't necessarily also going to have a huge increase in earthquakes or a change in shape and increased gas emissions. So they are not very reliable warning signs, and they don't always happen all at once, and it's not always very obvious, these warning signs. So how can we prevent volcanoes? There's really no way to prevent them, but we can try to mitigate the effects. So all volcanoes, at least in the US, will have danger assessment maps. So here's Mount Rainier, and you can see the red is showing where the locations might see smaller lahars. The yellow is where the location might see larger lahars. You'll notice that they follow the riverbeds. Remember, lahar is the ash mud when the explosive debris combines with water. And then the gray here is showing what would be affected by pyroclastic flows or lava flows. So you should know when you live somewhere, if you live near a volcano, where you are on the danger assessment map. Lava flows can also try to be diverted by building up steep slopes or levees to try to cause the lava to flow in one direction rather than another direction. So you can't necessarily stop the lava from flowing, but you can try and steer it one way rather than, say, towards a town or towards a neighborhood. Long-term hazards of volcanoes. Volcanoes have been really, really beneficial, as well as completely devastating. So there are some civilizations that depend on the volcanic soils. So that volcanic soil, that fresh soil that's created after these volcanic eruptions are incredibly fertile and very, very, very good for crops. So sometimes volcanoes are seen as a good thing in that way. Um, Other ways, not at all. So civilizations have been completely erased under volcanoes. So, for example, Pompeii, Italy, the town was completely covered by a volcanic eruption. So here are some photos of what that looks like. If you go to Pompeii, Italy, you can actually walk through what has since been excavated, which you can see the remains of the town and the houses and the people that were there during that eruption. So today, this was from Sunday this weekend. These are the current volcanoes. So we have no warnings or watches right now of our volcanoes near us. Everywhere near California is in the normal activity. These green triangles. There's a few in the Aleutian Islands that have an advisory, as well as Mauna Loa there in Hawaii. But as of right now, there's no watch or warning of volcanic eruptions, which is pretty cool. This is a USGS map. If you want to go online, I have the link right here. You can check, it's updated all the time to monitor all of the volcanoes that we at least have the ability to monitor. The white triangles here are unmonitored volcanoes. So it's pretty cool to go and see how things change over time, especially in the very highly active areas, which are these Aleutian Islands and Hawaii as well.